Hello, and welcome to my talk on the real stabilizer operators. So my name is Justin Makary. I'm a PhD student at Dalhousie University under the supervision of Dr. Neil J. Ross, or some of you may know him as Julian Ross. And so we also wrote this paper with Dr. Selinger of Dalhousie University. And yeah, I'm really excited to be in front of you guys. Ever since I was a master's student, I wanted to be a part of QPL in some way. So here we are submitting a paper. So I'm very excited to be here, and I'm excited to tell you about our work. So without further ado, let's give it a go. So yes. So we're going to take an introduction where we're just going to go through, kind of remind ourselves about what the stabilizer operators are, or what the real stabilizer operators mean, and a couple things about that. And then we're going to go into what we call type circuits, which are basically a compact notation for, a notation for to mixing wires of circuits, to basically enforce some sort of restriction to construction of circuits. We'll go over that, and then we'll use that to define our normal forms for our real Clifford circuits, and then we will go into the relations on these that we use to rewrite a Clifford circuit into its normal form. And this gives us, this will at that point give us a finite presentation of the real Clifford operators as in our monoidal category, or as a strict spatial monoidal groupoid. But it'll be very large, a lot of derived generators. There won't be in terms of the basic gates, and they'll be very large and redundant, and we would wish to basically trim this into a nice and compact presentation, which would have been given in the paper. So and I'll maybe describe a little bit about how this works, or how we had come to the trimming of our original large presentation. So yes, so the stabilizer operators, they're also known as the Clifford operators, and they play a fundamental role in the study of fault-tolerant quantum computing. They're very well studied. They're very famous. And my apologies. And they're generated under their composition and tensor product of the gates listed here. We have our scalar omega, and the Hadamard gate, the phase gate, and the controlled Z gate. And these generate the Clifford operators. And we're going to worry about the restricted subgroup of the Clifford operators known as the real stabilizer operators. And so you can imagine this as the Clifford operators, except pretty much, quote unquote, realizing everything. Our omega is going to become just our scalars -1 and squares to 1. And we still have our Hadamard since it's real, but the phase gate, we got to take the square of the phase gate, right? We're going to come out to the Z gate, and we still have the controlled Z. And these are going to be our generators. And so in the main content of the paper, and what we're going to go through is we're going to state our list of derived generators and suppose our normal form that's going to be built up for these derived generators. We could think of our derived generators as our blocks, and our circuits as our pictures we make with our blocks. And we're going to show that any automorphism of the real Pauli group can be identified to a unique real Clifford circuit in its normal form. So we can identify any automorphism of the Pauli group with some associated unique real Clifford circuit in its normal form that acts identical to it. And furthermore, if we're given some Clifford circuit, a Clifford circuit is an automorphism of the Pauli group under conjugation, so we can then find an associated normal circuit for any Clifford circuit you give me. And we're going to give our set of relations and state our rewrite system, state how we take any circuit over the basic gate set, any circuit in the real Clifford circuits, and how we rewrite them and filter them to our normal form. And then finally, like I said, this gives us our big presentation, but we're going to go through how we trim this to the more compact rule set, right? And so quickly, this is the real Pauli group, right? We have our real Pauli matrices. Notice that Y is missing since it's the complex one. You know, they're orthogonal, symmetric, they square to the identity. They're a very nice set of operators. And we have the real Pauli group on n qubits, just going to be basically the n tensor, right? Each of these are single qubit operations, and we're going to take the plus or minus of the n tensor of them. Each Pauli acts on a specific single qubit. Now, the real Clifford group, the one that we're considering, is going to be this normalizer of this real Pauli group. Yeah, so, and that's going to be the group that we're worried about. And since we're the normalizer, we have some nice structure that we'll expose later, or that we'll exploit later. And so this is the set of operators that we're dealing with. So next, one of the things that is in the paper, which I find to be quite nice, is the thought of typed gates. So we wanted a way to basically signify the restriction of our compositions, and the typed gates was a way of doing this. They were originally chosen to be certain colors to match, but for accessibility reasons, we have chosen the double bars as we see here. So the single lines are just of a single simple type, we call them, and then the double lines, we'll call them a double type. So when we compose our circuits, we want our double types to fit with double types and simple types to fit with simple types. So we've kind of visually signified a way of how circuits can fit together. So for example, if we have our G1 and G2, we see that they have various simple types and double types on their wires. If we want to compose them with G1 first and G2 following to the right, we can do that because the top right double type of G1 will match with the top left double type of G2 and everything, right? But the other way around is not going to work because, as we see, the double types do not fit together, and this is, so to say, not a well-formed circuit in our formulation. So, and then furthermore, we introduce a notation where if we had types of gates, if we wanted to put gates into certain classes, maybe we call them G gates and H gates in this case, we have two of each, I can write a nice, concise way of describing the family of circuits that are a type G gate followed by a type H gate, and such that it's well formed, right? Such that the types of the gates are going to mix. So that diagram right there, GH, is actually just to signify the two circuits at the bottom, namely G1 followed by H1 and G2 followed by H2, because those are the circuits that we could form in that type arrangement. So we'll see this used to describe our normal forms. And with this, it's time to state our derived generators. These are going to just be these are our little building blocks that we're going to use to build up our normal forms. They were chosen based on their actions, which we'll go into a little bit later. So here's the first set. We have A gates, B gates, C gates. That's what we see here, D gates and E gates. A through E gates are all of our derived generators that we'll use to build our normal forms. So first we notice a little bit of redundancies, right? It's like A1 and A3 are the same, B1, B5, etc. These are the same. And that's what I mentioned about when we wanted to, so when we make our normal form, we can kind of essentially think about this as taking an operator and fanning it out to a bunch of local interactions. And when you do that, with our typing arrangements, there's a bit of restricted way that some of the things fit together in this real group, as in contrast to the complex for example, in the complex Clifford group, we know that we can conjugate any of the polys to the other. Namely, I know that I can conjugate x to y, or y to z, or z to y, but I do not know the same thing about our generators of our real poly group. Namely, I don't have a real Clifford that will conjugate an xz operator to a z operator, or vice versa, right? So there's a little bit of a restriction there, and that comes up with the choice of gates that appear. And so they look redundant now, but they are made non-redundant when we type them, right? So these are generators. We go in 2 steps. Here is the definition of our generators, right? Definition in terms of the basic gates, the basic generators of the real Cliffords. But now we can apply a typing to these gates and use them to build our typed circuits. So we see that A1 and A3 were the same, but they're going to be typed differently. This is with respect to their action. A1 was chosen to keep Z, Z. A2 was chosen to change X to Z, and A3 was chosen to keep XZ, XZ. Now, both the identity can do both of those things. So, but the XZ appearing will signify something different to us, and it will have a distinct structure to its ladder. So, so this is where the typings were made. So so we see that only the A's and B gates are typed. Everything else is just or that. When I say typed, I mean involving a double type. Otherwise, we just have simple types everywhere. And we're going to use this to define our normal forms. So we have our derived generators, which are our little pieces, and then we kind of build into our medium pieces, which are going to be called Z circuits and X circuits. And they're named perfectly in the sense that a Z circuit is a sort of ladder that is going to carry a Z all the way up the ladder. And I'll be more precise in that in a little second here. And X circuits are a down ladder that are going to carry an X down a ladder from kind of the top qubit to the bottom qubit, and vice versa. Here, carrying a Z from the bottom to the top. And so it's kind of a fanning across all of our qubits into more local interactions, right? We see only on single qubits or 2 qubits. And we will, and I'll describe a little bit about their action choice a little bit later. But the idea was that we had to take certain poly operators to the generators, like an I, an X, a Z that appear across all the qubits, and these will allow us to take any, with our choices of A, B, and C, we can take any poly that squares to the identity up to just a Z in the top and I's on all other qubits. So we'll see that a little later. And then if we're fanning up and down our qubits, this is the idea of the normal form. As I fan all the way across all n qubits, then recurse up to n-1 qubits, and so on. So we have a Z circuit on n qubits, X circuit on n qubits, Z circuit on n-1, and recursively off. And we with this fanning process, we can maybe already start to look forward to the fact that if there's going to be some sort of filtering here, right? If there's going to be a filtering, maybe it would be nice in this fan process when we filter to make sure that nothing makes it to the bottom qubit here. That would kind of be an assurance that if I'm going to filter my way up this kind of fan up and down, and every time I push stuff through with our relations, nothing makes it to the bottom qubit, that's a very important thing, right? Because we're going to recurse all the way up and everything is going to end up being pushed through or absorbed. So that's it's an interesting thing to note, or like keep it in mind. And so then we have some existence theorems, and these are around our Z circuits and X circuits and their properties and how they act on specific polys. This is a little more rigorously described in the paper, but these are anchor. These are kind of very specific, like anchor points of our automorphism, right? Because they're the Z tensored with I, and you can imagine Z across all the qubits are going to be these generators, and it's nice to anchor these points down and know what and have a unique Z circuit that brings us there. So we know that for any Pauli that squares the identity, I can craft a Z circuit that will take it to the Z up to the top, like I stated. And then the theorem, and then the second one says the X to the bottom for the X circuits. Note that Q has to anti-commute with Z, which will be which is more of a condition where if I'm anchoring to points Z and X, and they anti-commute, and so if P and Q anti-commute and we move them to I and X, those anti-commute and automorphism, etc. So let P and Q. So then the final one is that these X circuits and these Z circuits kind of work together. Namely, the Z circuit's able to do its job on P, and the M circuit does not affect that, and the M circuit is able to do its job on Q, and the L circuit doesn't affect that. So, well, when I say doesn't affect it, I mean on the right-hand side, we the ML conjugating Q, we receive exactly IX, right? But ML, L will push the Z. When we apply L to P, we'll arrive at Z tensor I ... But the M will then push the Z all the way down. It turns out M circuits push X's down and Z's down. And then this is kind of our big theorem that we'd want out of this to be able to describe our automorphism of the Pauli group with these normal circuits. So this is our big theorem. So yeah, like if there's any automorphism in the Pauli group, we want there to exist this normal circuit C that acts the same as it. And as previously stated, since a Clifford circuit is an automorphism of the Pauli group, this is good. This will be good for us. So that's what I said here. So another thing to once you build out the normal forms, and I guess if you were to believe me that these are in fact the normal forms, then we can count them, and it's worthwhile to count, or at least interesting to consider how many things are in this. So Neeb would have came up with a count for this as well, but he did so with other manner, and the formula looks very different, but as far as we can check, it's the exact same thing. So that's also something, is that there could be two known representations of the count for this that seemingly did count it in different ways and end up to the same number. So that's interesting as well. Most of this is just kind of a counting argument on the appearance of certain gates. So the original, this is actually worth mentioning. With the original thing we have these type gates. The type gates is actually kind of in the second, is in the gamma stage, so to say. The beta or alpha stage was actually just the number of occurrences of certain gates. So it turns out if you want to map Pauli operators that square to the identity, and you want to map them to just a Z on the qubit at the top, you can start at the lowest non-identity qubit, apply something to make sure that it's changed to a Z. In our case, that's the A. We can change, well, we can keep Z Zs, we can change X to Z, or we have XZ now instead of Y. We can't convert Y to Z, we can't convert XZ to Z. But if you've read Dr. Selinger's paper, he was able to, since he has the power of the complex Cliffords, he can conjugate Y to Z and proceed. But here we realized that we might have to keep xz around. So if we're keeping xz around and trying to push it up, there's going to have to be something to account for. Well, since p squared is I, there's evenly many xz's, so there's a sort of cancellation process. It turns out there's an evenness and oddness on the appearance of the B4 gate. And the B4 gate, in the actions, if we look, is the one that takes xz and z and gets rid of the z and keeps xz along up the ladder, so to say. But B8, the one that does the exact same action as it, but is typed differently, cancels xz's for z. So that is the, if there's evenly many xz's, push them up until they reach a next xz to cancel them off. There's a very kind of, so there's an even and oddness conditions on the appearance of those. And so you can count them in this manner. And so instead of the even and oddness conditions, since we wanted something a little bit more, whoopsie, I passed it. Since we wanted something a little more concrete to deal with the rewrite rules, we chose typing, the coloring scene, or the typing here, right? Because instead of an even and oddness of appearance of B4s, we can do it by swapping back and forth between type 2 and type 1 along our ladder. So, which I thought was nice, and we'll see, because then that will make its way into the possible rewrite rules that we can do, or need to do. And so now we're ready to present our rewrite system. And so we were previously stated that these circuits can be identified to the real, unique real Clifford circuit in normal form, but we want a system on how to do this, right? So we're going to rewrite them. And what we're going to start with, well, maybe we don't start with this. Maybe we start with just a regular circuit. And then somewhere along the way of trying to make this standard real Clifford circuit over the basic generators into our normal form, we get something that's close to a normal form. Maybe we'll call this a dirty normal form. It's in the normalization process. And then if we can show that any one of these dirty normal forms can be converted to a normal form in finitely many applications of our relations, then, well, then the only question left would be is that, can I make every circuit a dirty normal form? So let's first take what I mean by dirty normal form. This is our circuit. We have them a little spaced out like this. You'll see why. It's to leave some room for some numbering. So we have our Z circuit ladder up, the D circuit ladder down on n qubits. We recurse on n minus 1. A dirty normal form will be formed from this labeled normal form here. We have numbers, right? So these numbers are going to signify what would constitute a dirty normal form, as in it's something that looks like a normal form with possibly some extra gates on these numbers, and they're according to this scheme here that we place. An H gate can only be placed on wire 1, we place on a wire with the label 1 and or the label 2, or a double wire with label 2. You'll even see that a couple of these have a difference based on whether it's a double wire or a single wire. So that is how we're going to build. So our dirty normal form is anything that in these numbers could have possible gates according to these rules. Now, these rules are they're not out of nowhere, so to say. If we were to take a whole normal form and I were to want to push basic gates through it or something, if I want to try rewrite basic gates possibly from left to right on these normal forms that we see here, there's actually a relatively limited amount of interactions that can happen, right? We're a ladder up, a ladder down in some sort of a block form. Our basic gates are either no qubit, all single qubit, or the one CZ that acts on 2 qubits. So you can imagine that there's actually a limited interaction of the things. We can write down all the ways that some basic gate will progress from the left on this on a standard normal form. Now, the rewrite rules where number 1 differs from number 2 is that possibly when I rewrite something from 1 past A, I get something else that could possibly be a 2, and so on. So when I go past A, I kind of change my behavior to the 2s up the ladder. Then we pass C, change our behavior to 3. When we hit D's, we go change our behavior to 4, so to say, to go down the ladder. And the nice thing, the thing that I desired or mentioned earlier, notice that there's no numbers past E. No, in this rewrite, the goal is to have nothing make it past E, so that so if we were to push everything through, everything is moved up qubits, and it continues to do this up the ladders. And so in the end of the day, we will be left with just a normal form. And so these are a couple examples of the rules. I must have mistaken to change this color here. They were originally colors, but for accessibility reasons, we changed them to the double bars. So I apologize about that. So these are a couple rules here. This is what I'm talking about, where if I have a single qubit basic gate, right, like a Z, a C, a Z, a H, right? If I want to push a Z or an H, it's either going to appear, if you look back at my normal form, it's either going to appear, well, it'll have to be on an A, it'll have to be to the left, directly left of the A, or directly left to, well, the top side of the B, right? Or if something makes it past that A, then we're going onto the bottom side of the B, then we're going to have to make sure that we accommodate that too. And that's where the number 2 would come in versus 1 here, is to say there's a certain restriction on what makes it past A. And so with this, we're kind of describing our filtering, right? Our way of pushing through with these rewrite rules. So the lemma we desire is that any dirty normal form can be converted to its normal form by, applying finitely many relations present in the diagram. And we'll use it to prove this theorem, right? So this lemma, you'll have to take on Word or read through the full details of the paper, right? But if we take this one, the theorem. So if I can write any dirty normal form into a normal form, the question left to answer is, can I take any circuit to a dirty normal form? And cleverly enough, the answer is yes, because, well, we just tack on the identity has a normal form. So we're just going to, you give me any real Clifford circuit over the basic generators. To the right of it, you put the entire normal form for the identity. And now we have a dirty normal form, in which we apply our lemma and we receive our result. Our goal was to trim this down to, if we were to just give a presentation of the real Clifford operators in terms of the basic generators and some more seemingly natural, smaller, basic, compact rules on these basic generators. I mean, the search in some sense begins with just, well, we have a presentation, it's large, and if we were to just take so we know that if we can take all the relations that we have there, if we were to replace all the derived generators with their definition in terms of basic generators, and then we were to have a rule set to which I can act on those and derive all of my relations I had before, then we're good to go, right? So it's a big task, but that's somewhere to start, and we can also give ourselves some basic relations involving the generator, like the real Clifford operators that we would kind of know and more familiar, namely that the Z moves past CZ and little things like this. So you can start yourself with a little group of things and a direction to go, and then from here we kind of start deriving the easy rule first, maybe the ones that just involve Z's past thing, no 3 qubits, nothing, and so then we can continually reuse these as the rest of the process goes on. Unfortunately, I don't have. I really wish I had more of a more automized way that we generated these. If there was was not done by machine proofs or anything like this. It was some sense of a structured thing of knowing what you're looking for, pushing the rule, applying your rules, knowing that I have to clean up everything to the right. Yes, and in total, I guess this means that we've defined a normal form for real stabilizer circuits, and we've shown that every stabilizer operator admits a unique normal form. And we've introduced this set of relations that suffices to have this rewrite system that we talked about. And, well, this itself yields a presentation by generators and relations of the real stabilizer operators. But furthermore, we trimmed it to the nice compact set that you're going to that you see at the end of this paper, right? That the real stabilizer operators can be described by the basic generating set and these 16 relations that we describe here. And we see that, you know, the first couple, like I said, are kind of things that we can kind of give ourselves to know to move on. And then I guess a little bit of the only question is you start to need things and then you add them, and then the worry is, well, am I missing something, or did I add too much and we're not compact anymore? So you have to use with care. Let's see, for this one, so CZ, we know that this is essentially that H is going to swap qubits with a swap. The fact that X's, or sorry, the fact that Z's or anything like this were to move through CZs and these is no problem to us, but we did not have some way to know what we already know, that H should swap on that swap, so we have to include it. And then these they look a little mysterious now, but if we see the more alternative set of relations that we've given here, where we give them in terms of the more derived generators, where we see our X's and CX's, right? And the real Clifford's in its full glory, we see the that they're maybe a little bit more intuitive than they seem up there. That there should be there's the condition with these CX's swapping around, and these are a little, but these may have very specific uses. So yeah, and another thing to note is that only the 2-qubit rules would have changed from Dr. Selinger's paper to now describe the new subgroup, right? The 3-qubit rules stay exactly the same because they're all real. It's just that we had to accommodate the way to do the qubit rule, 2 qubits, and how that would fit with the 3. So, but yeah, so we trimmed it down, and I'm pretty happy with it. So, and I'm also, yeah, and I'm pretty happy that I got to sit and tell you guys about it. So if you made it all the way, I really appreciate it. I honestly do. I appreciate you just sitting in and listening. And if you have any further questions, there's going to be a comment section here on this YouTube video. Feel free to comment and reach out to me, and we can have a chat about anything that you you know that might be of interest to you. Or you can reach out to me on my email. That works as well. Just justin.makary@dal.ca. You can I'll maybe leave that in the YouTube section as well. But I appreciate your time, and thank you for coming to QPL, and I hope you enjoy the rest of the conference. Thank you.